Okay, so one of the things to talk about with respect to streams, before we go much further, is a quick introduction to flooding. So we talked about rating curves, which basically allow you then to take any given height. If you just if you have some sort of record, some sort of measurement device that tells you how deep the water is at any given point in a stream, if you've got a rating curve there, then you can just go over and determine the discharge, right? So here is stage, and here is Q, and we said that it looks kind of like this, right? So if you want to know what the volumetric flow is, you don't need to do all these crazy calculations looking at the depth of the water and the width of the stream and measuring the velocity. Uh, a rating curve, assuming that the shape of the stream channel at some point doesn't change, simply means that all you need is the stage, the height, and from that, use whatever equation is used to define this line, but out comes the volumetric flow, right? Which is a pretty handy thing to have. And so if you might have driven over by a stream at some point, and the stream has a little gauge sticking up out of it, right? So the stream is like this, and the gauge is just a piece of metal, but it's demarcated into different elevations, right? So 0, 9.1, 9.2, 9.3, and so forth. So this would be height above whatever the datum point is, the bottom of the stream or whatever. So if somebody wants to know what's the volumetric flow in this stream, they just run out and take a look at this, and they say, oh, it's at 9.0. That's the stage height. They go to 9.0, and out comes the volumetric flow, let's say 1,500 cubic feet per second, something like that. Okay, there's another kind of graph that we should talk about related to streams. It's called a hydrograph. And a hydrograph is just a chart that tracks, you can do it as stage, or you can do it as Q. We'll do Q here on this axis versus time. And so, of course, you're just seeing the water in the stream just sort of cruising along at a given point, given level. It usually just very, very slowly falls over time. Then you get a big rainstorm or something, and what happens? Well, the height of the water in the stream rises and then begins to decrease again. Right? So that's that's maybe a flood, and we'd expect maybe the rain event occurred, somewhere in here, and that caused the water level in the stream to rise. So I'm using Q over here. Remember that Q is basically easily related to stage, or the height of the water. So how much water is flowing down the stream versus the height of water in the stream. Those are kind of interchangeable for our purposes here. So you can think about how much water is flowing down the stream, or you could think about how high the water level is in the stream. It doesn't really matter. We're going to use Q on this axis for now. And remember that the units are, in the States, are QFS, right? Cubic feet per second. I assume that in other places it would be CMS, most of the rest of the world, cubic meters per second. All right, well, it turns out that if you have no changes to a watershed and no changes to streams and so forth, and those kinds of things do happen, then sometimes a lot of times the shape of the hydrograph after a flood follows a sort of a predictable pattern, and we call this recession, flood recession. The flood recedes, and the way it recedes is kind of this exponential curve. If you've ever dealt with radioactivity or biology, like ecology, exponential change is a really important part of all that. So this is exponential decay, the shape of this curve. It's kind of, basically what it's saying is that the slope, if you just sort of draw tangents to this line, the slope keeps getting less and less over time. It's really steep at the top, it's moderately steep in the middle, it's less steep at the bottom, and then goes back to more or less being horizontal, right? So the rate of change is changing. And because it behaves that way, well, then we can use equations developed for exponential decay, including through radioactive isotopes and so forth, to model this. And the generic equation looks something like this. I'm going to write it out and then I'll explain it. Q equals Q naught e to the negative AT. All right, so write that down. Q equals Q naught e to the negative AT. So what is Q? Q is the discharge at some time t, whatever that time is. So we could even put a little t there, QT. Q naught, that little zero is pronounced naught, is the discharge at the beginning. And you can define where the beginning is, but you'll see how this works in a second. A up here is referred to as a decay constant, and it's a number. And that decay constant we'll calculate in just a second, but that decay constant basically is just telling us how fast does the stream, does the discharge or the stage, how fast does it kind of go back to being normal after a flood? Does it take a long time, in which case this curve would be stretched way out here like this? Does it take very little time, in which case it drops down, or is it sort of in the middle? T is time, and then E is this, this natural log. It's the base of the natural log, which is just a number. Okay, so what we can do is we can experimentally derive A. Okay, so there's Q and there's time. And again, the way to think about A, right? We need to, what is A? What is A? A is sort of like, you can think of it sort of like the half-life of a radioactive isotope, right? So how long does it take for a radioactive isotope to decay? That's kind of like what A is. How long does it take for the water level in the stream to drop back down to where it was? And we can determine that experimentally, right? So let's say we're measuring this stream, this hydrograph, and we find out that that the peak flood right here, that's peak flood, is equal to 5,000 cubic feet per second. So in other words, if I draw a little dashed line over here, this would be 5,000 CFS. All right? And then we find out that 40 days after that time, so I'll drop this down, 40 days later, right here, this is 40 days. This was 0 days. This is 40 days. At that point, the Q is 4,000. So this is 4,000 CFS is this point right here. 5,000 at the peak, 4,000 40 days later. And this is just done through observing the water level in the stream after a flood. So what we can do now, right, is we can solve for A, because we know everything else. We know that Q equals Q naught e to the minus AT, right? So therefore we know that 4,000 CFS, that's this after some amount of time, is equal to 5,000, that's the peak flow, times e to the negative A, and t is 40 days. All right? So we have this equation. This equation here is just this equation with some numbers plugged into it. So we can divide both sides by 5,000, and we get, what is that, 0.8 equals e to the minus A times 40. And if you haven't done this sort of thing in a while, to get rid of the base of the natural log, you take both sides, you take the natural log of both sides. So you'd have natural log of 0.8 equals, and when you take the natural log of the base of the natural log, the e just disappears, and you're just left with negative A 40. So then you divide both sides by 40, and you get, let's say by negative 40, and you get the natural log of 0.8 over negative 40 equals A, which equals 0.0056, something like that. Okay? If you don't have a calculator at home, first of all, you can just Google, what is the natural log of 0.8 or whatever. But I'll show you a little bit later how to do these calculations in Excel, so that it makes it a lot easier if you want to do that. Okay, so now we have A. Is that still visible down there? I guess it is. Now we have A, and so who cares, right? What good does that do us? Well, now essentially what we have is the inherent characteristic that tells us how fast the water is going to decay away. So if you have that, maybe now you want to say, let's imagine that there's some homes here along a riverbank. It's a community. Those are supposed to be homes. And they are currently underwater, right? When the water level rose up to 5,000 cubic feet per second, the water rose up out of its banks and flooded those. And we know that people can return to their homes when the water level drops down to this point, right? Which, let's say this is 5,000 CFS. Let's say this is, 2,000 CFS, okay? So when the water level in Q, the discharge, drops back to 2,000 CFS, then people can return home. How long is that going to be until they are able to return, right? So those are some examples of what kinds of equations or calculations we might do with this information. Well, let's come back to that in a second. Let's do this one. Let's say, before we get to that, let's say, what will the discharge be not after 40 days, but be at 100 days? What will the discharge be not after 40 days, but after 100 days, right? Well, you could kind of maybe ballpark it here, but we can calculate it directly. So we would say Q, that's what we're solving for now, right, is the discharge. That's supposed to be Q naught, sorry. Q equals Q naught e to the negative AT. We want to know what the discharge is at 100 days. The peak discharge was 5,000. That's Q naught. E to the negative A, which is 0.0056. And the time is 100 days. So what do you get? Q equals 5,000 times e to the negative 0.56. And if you do the number crunching, you get, I think, 2860 cubic feet per second. So after 100 days, the water would be somewhere up in here, still too high for people to return to their homes. When will they be able to return to their homes? Let's see. What do we need to know? We know that Q equals Q naught e to the negative AT. And what we're now looking for is time, right? How much time will we have to wait from peak flow until the Q is low enough that people can return to their homes? And we said that people can return to their homes when Q is at 2,000 CFS, right? So this is negative, what is A? 0.0056 times T. We divide both sides by 5,000. What is that? 0.4 equals e to the negative 0.0056 t. You take the natural log of both sides, negative 0.0056 t. You divide both sides by that number. And the amount of time people have to wait until they can come back and start cleaning out their homes is equal to that. And I don't have that calculation in front of me, so I'm going to hit pause. Let's see if I can hit pause. Am I allowed to hit pause on this thing? I don't know. Well, anyway, let's see if I can do it really quickly. Let's see if I can do it while you guys wait. That's not fair, but natural log of 0.4 is negative 0.92 over negative 0.0056. So let's see if I could do that. 0.92 divided by 0.0056 is equal to 164 days. So these poor people are going to be out of their homes for 164 days until water levels drop back to the point that until the water is now back in its banks and the roads and the homes are exposed again. So anyway, that's a technique for calculating flood recession curves.